Hello everyone, in this video we're going to talk about how to find the volume of solids of revolution. Now we're going to look at the first case, which is called the solids of revolution created by rotating a curve about the x-axis. We're going to have a look at what that actually means. Now here I have a curve. I'm not going to use entire curve, but I'm going to use half of them. As you can see, the solid line on the right hand side in the first quadrant. Okay, so we're going to rotate this one about the x-axis. I'm going to show you what it looks like as an animation. So you can see on the left hand side, you got a black curve. We're going to rotate it about the x-axis. As we are rotating it, we actually can create a solid. And now you can see what it looks like. And I'm going to change the perspective a little bit so you can see more clearly what it looks like. Now, just notice that because we have one curve rotating around it, so that means the middle of the shapes are actually not hollow, it's a solid shape. Okay, so please make sure that you actually have a right perspective, it's a solid shape. Now, so we are going to rotate it, but how are we going to find the volume of this solid? Now, this is called disk method. What that means is we're going to actually cut it into a really thin slice vertically. So I'm going to show you what that means on the left hand side. So we're going to stop the rotation. So we're going to actually cut it into thin slice. You can see the green color bits. And just imagine that the slice can be thinner and thinner and thinner. And if we start to rotate it around, as you can see, lots of mini discs actually together will form this solid 3D shapes. So this is our approach. So you can see on the right hand side, I show you one slice of that. And we're going to actually go further, just have a look how this disc can actually help us to find the volume. Now, firstly, we want to find the volume of the one disc. So as you can see, you need to have, this is actually a cylinder shape. So for the cylinder shape, it's the cross-section area times by the depth of the cylinder. So the cross-section is a circle, so we need to know the radius. So we do need to know the radius from the center to the edge. So we're going to look at the graph here. So the center is here. So we're going to use the most far right hand side. From here to the edge of the curve is our radius. And this length is actually represented by the y value. I call it f of x. Okay. Now, this is our radius. Therefore, the area of the circle is pi r squared times by depth. So we replace the r with f of x squared times by depth. So let's have a look at what depth is. So that here is the depth. And what does it look like on the graph? So imagine you have a thin slice like this coming all the way down here. Now, in fact, this is actually changing x values on the graph. So instead of delta, we're going to say f of x squared times by dx. Okay? Now, this is just one slice. In order to find the entire volume, we have to add all of these slices up. So imagine you have one disc here, and you have next small discs here, and next one here, and next one here. So keep going. As the discs getting thinner and thinner and thinner, it will be getting closer and closer to the original solid. So therefore, we're going to use the integration, because integration means that adding all these small slices up. So the actual volume is the sum where you start the curve. For this case, we say we start from A, and where you stop the curve, B, and then adding all the volumes up, which is f of x squared dx. Now, obviously, pi is the constant, so therefore we can take the pi out. So we can say it is pi integration of a to b f of x squared dx. This is how you find the volume of the solids of revolution rotated by a curve about the x-axis. Let's have a look at this question. Determine the volume of the solid of revolution when the curve y equal to x squared, the boundaries given x is between 1 and 3, is rotated about the x-axis. So let's have a look at what does a picture look like. So I'm going to quickly draw. It's a quadratic and it's from 1 to 3. Okay, so I'm going to say 1, 2, 3. My boundary starts from, finish here. When say x is 1, y value is 1. When x is 3, I'm going to say bigger than 3 squared. So this is 9 here. So I'm going to just briefly draw a curve here. So this is what it looks like. It's really not to scale, but just really clearly try to show you when we rotate it by x-axis what it looks like. So I'm going to rotate it by x-axis. So that will give me a solid that will look like this. So that's the solid. Okay, so again, remember we're going to use the disc method. We're going to cut them into slices. So we have many slices and then it creates a lot of cylinders. So each cylinder is pi r squared h, which times by depth. So the depth is change of x. We use delta x. And your r is literally represented by this y value here, so which is your x squared. So I'm going to say, and then we're going to add all slices up. So we're going to use the integration sign. You're starting from 1, finish at 3. Pi r squared, your r is your x squared, and then your depth is delta x dx. Okay, so now you can take the pi out from 1 to 3, x to the power 4 dx. So all we need to do is to integrate. So therefore you have x to the power 5 divided by 5, 1, 2, 3. And all you need to do is a substitution. So you have 3 to the power 5 divided by 5 minus 1 on 5. So which is 242 on 5 pi unit cubed.